Good morning to all. Today we are going to start Unit 3 for our subject Computer Organization and Microprocessor. In the previous unit, we have studied in detail about 8086 microprocessor, its architecture, its register organization, its memory segmentation, and what are the different modes we have in the 8086 microprocessor. In this session, we are going to start the assembly language programming with 8086. So, in today's world, the computer programming has evolved a lot from low level language to high level language. So low level language is nothing but machine language. Medium level language is assembly language, and high level language which we are using in nowadays, which is C++, C, Java, etc. etc. Okay, so in the previous earlier days of the computer, they were using only the low level language, which is machine language, which also we can call as the binary language, which understands only zeros and ones. In the middle level language, it comes as your assembly language. When we are writing this assembly language, the computer processor will not understand this assembly level language. It need to convert into a machine level language, machine understandable language, which we are doing with the help of an assembler. So machine language, what is a machine language? Machine language is nothing but is a low level language. So computer can only understand only the language of digital electronics, nothing but zeros and ones. Zeros and ones, right? So that's why we are also called this machine language as binary language. So digital electronics deals with presence and absence of voltages. If it is presence of voltages, it will be giving us plus 5 volts. Absence of voltage will be taken as 0. So nothing but plus 5 volts, nothing but high, 0 volts low. So within the computer, there are two logics that will play their role, and they are positive logic. Second one is negative logic. Positive logic, nothing but here the presence of voltage will be denoted by 1 and absence of voltage will be denoted by 0. Positive of voltage denoted by 1, absence of voltage denoted by 1 is termed as positive logic. Whereas the second one, which comes as negative logic, here presence of voltage will be denoted by 0 and absence of voltage will be denoted by 1. So these two are the positive logic and negative logic that will play their role in this within the computer. So as I told to you, machine level programmings, they will be understanding the machine understandable format, nothing but zeros and ones. So how to understand that machine coding by the user? So it will be the machine level programs will be in the form of what? In the form of instruction sequences, or in the form of instruction sequences, nothing but they will be in the sequences form, in the sequences of ones and zeros. You will be clearly understanding how this instruction sequences will be in the coming few minutes. This can be even be hand coded. We can write on our hand external byte by byte and executed on an 8086 based system. So due to the complex instruction set of 8086 and its opcode conversion procedure, so due to why programmers prefer this assembly language is, as we have in our 8086 system a very complex instruction set. We have many instructions, we have n number of instructions which 8086 uses for performing its task, and its opcode, for each instruction there is some opcode, nothing but operational code. There will be some code which is understandable by the machine language, so we need to convert this opcode for each and every instruction. So most of the programmers will be preferring this assembly level language. Clear? Machine level programs are nothing but they are in the form of instruction sequences. They are in the form of some ones and zeros which are being coded in some opcodes, in some registers, in some memory. You seeing this one by one. So for an example, if we see a program, write a program to add a data byte. We need to add a data byte located at offset address. What do you mean by offset address? It is in one of the segment address, and in that segment address the offset address. So offset address is 0500 in the one segment address which is 22000. Nothing but the segment address is 2000 into 10 plus 0500. So totally we will get as 20,500 H to another data byte available at 0600H in the same segment, and store the result in the 0700H in the segment. This is the question. Think but the question is, we need to write a program to add one data byte in one corresponding offset address in particular segment, and another data byte available at 0600. So we need to add first data byte and the second data byte present in offset address 050000H and at 0600H, and store the result at 0700H in the same segment which is 2000H address. So what the thing I need to write? This is the assembly language. So move is one operand, and it tells what it needs to do. This is the register and this is the address. So this is my source and this is my destination. So what the thing move AX is a 16-bit register, so we can able to 2000H value is being stored as AX, right? And whatever AX is being stored is moved to your data segment. Okay, now AX has 2000H address value. So what I need to store? The offset address, what? See, 0500H, if you write without brackets, it will store that value. If it is in the brackets, it will assume that inside this address value, whatever the data byte we have will be moved to AX register. Similarly, now add is one more operand which is used to add two instructions, AX comma 0x00H. So what the data byte you have in 0600H will be added with the byte present in AX, and the result is in now AX. Now what I need to do? I need to store the result at 0700H in the segment. So what I need to do? I need to move whatever the data byte is present inside the address of 0700H, and at the end you need to end the program. This is a simple program. what we are using by using a assembly level language. Store the data, add the data, and again store the result at the corresponding location. So how they are being opcoded, how they are being coded in the machine understandable language, right? So for that one, we need to understand what are the various instruction formats we have in our 8086 microprocessor. See here, so this is how you are converting assembly language instructions to machine code, right? So how the machine will code for the assembly language program. So as we have seen in the previous slide, we have some assembly language instructions. This is first instruction, second instruction, third, fourth, fifth, like that, depending upon the program, the number of instructions you need to code one by one at a time. So how to code? First thing is we need to know the instruction formats. So an instruction can be coded with 1 to 6 bytes. 1 to 6 bytes. Nothing but they will be having a 6 bytes of an instruction can be have 6 bytes of information. 6 bytes of information. Okay. So each will be byte 1, byte 2, byte 3, byte 4, byte 5, byte 6. Right? So here you can see a box which has opcode, which has data bit, or I can call as direction bit, and W is width of the data. Getting a point here? Getting a point here? Right. Now how much data it has, and what is the direction bit, whether it is a source or destination, or the data flow to the register field from R by M, or data flow from the register field to the R by M. Getting a point? Right. So byte 1. So what is this instruction format? The instruction format consists of basically two fields. Basically consists of two fields, which are opcode and operand field. Opcode, what it does, this field specifies the operation that has to be carried out by the CPU. Opcode, what it defines, it tells the CPU what it need to be done. Operand field, nothing but this field contains information like memory locations, values, registers. So based on the operand information, CPU executes its instruction. Okay, so the opcode field 6 bits specifies the operation such as add, subtract or move. The register direction bit D bit tells in which direction the registers need to source or destination operand. So if it is 1, the data flow to the register field from R by M. R by M means register or memory. Clear? 0 means data flow from the register to the R by M. 1 means data flow to the register from R by M. If it is 0, it tells data flow from the register field to the R by M. And the next one is W, which is width bit, or I can call as size bit. If it is 0, the data size is 8 bits. If it is 1, it is 16 bits. Clear? This is 1 byte instruction which always consists of opcode and operand. Next, byte 2. Second byte has two fields. Second byte has two fields that are more field. Second one is register field, and the third one is R by M field, which is register or memory field. So it has 2 bits, it has 3 bits, it has 2 bits. So here in the first byte it has 6 bits, opcode will be of 6 bits, data bit or direction bit will be 1 bit, width bit will be 1 bit, mod bit 2 bits, register field 3 bits, R by M field 2 bits.